start. Good afternoon, everyone. Welcome to week 11 live session on structural dynamics. I'm Danish Bashir from IIT Madras. So, week 11 is live, going on live on the NPTEL website, in which the modules continuous systems are being discussed. Therein, you study the vibration characteristics of continuous systems, beams, columns, bars, where the mass is not defined at single degree, or I mean to say that mass is not discretized as at the degree at the points where the degrees of freedom are defined, but it is continuous throughout the domain of the body. So for those types of systems, you need to study a different type of dynamics, and it is studied in the module dynamics of continuous systems. But in today's live session lecture, we will be continuing our discussion that we left last week on multi-degree of freedom systems, wherein we solved some numerical problems related to 2 degree of freedom system and 3 degree of freedom system. So, continuing from that thing only, today we will see some more important concepts in the dynamics of multi-degree of freedom system. Okay. So regarding to the multi-degree of freedom system dynamics, I already told you what are the stiffness matrix, and so in the stiffness matrix, I told you, for example, we write stiffness matrix K stiffness matrix we write by elements Kij. Okay, where I told you it is actually Kij is the force produced at ith degree of freedom when we give the unit displacement at jth degree of freedom, and all the degrees of freedom are given zero displacement. Uh, I is the degree of freedom where force is produced. Force is produced, and J is the degree of freedom where displacement is given. And what is the special in this displacement? It is a unit displacement given at the jth degree of freedom. Displacement is given. Okay, unit displacement. And there is one more matrix that is common in this multi-degree of freedom systems, that is the flexibility matrix D. Okay, it's nothing, it's but the inverse of K matrix, stiffness matrix K. Okay, and it is written as, its elements are written as Dij. Okay, so it is the inverse of this thing. So what will be the meaning of the Dij notation? It will be simply the displacement produced at ith degree of freedom when unit force is given at jth degree of freedom and zero force at all other degrees of freedom. So you have to just invert the above definition to get the definition for Dij component. So here in ith degree of freedom is displacement produced. Okay, it is displacement produced at displacement produced at okay, not it's only displacement produced at ith degree of freedom. It's obvious from the notation. Displacement produced, and J is similar to above one, but you have to invert the things. Okay, it is displacement produced due to unit force zero force at other DOFs. Okay, degrees of freedom. So this is just I think I want to remind you people what's stiffness matrix and flexibility matrix. So if we are required at in point of time, and I also told you one more important property about the stiffness matrix is its transpose is equal to the matrix itself. That is, it K is symmetric, and same is stiff flexibility matrix is also stiffness, because inverse of a stiff symmetric matrix is also a symmetric matrix. So both K matrix and D matrix are symmetric in nature. So in any case, if you are asked to prove how you can prove that stiffness matrix is this symmetric, so let's discuss that one first. Okay, property. That's the property, in fact, of property one. Property. Okay. So in the property we have K matrix is equal to the transpose of itself. Okay, K transpose. Stiffness matrix. Matrix is it is symmetric in nature. Symmetric in nature. Okay. So let's try to figure out how it is symmetric in nature, how mathematically we can formulate it to show that K is equal to K transpose. So let's see how we can do that thing. So I already told you K and D are inverse of each other. So I can write K is equal to D inverse, or I can write K times D matrix is equal to identity matrix. Okay, identity matrix. Okay. So let me mark this as equation first, okay, so because we will be using it in the later period. So this is one. And one more thing is one important relation you people know that force is given as a force vector. Since you have to keep that in mind, we are dealing with multi-degree of freedom system. So everything here will be in the terms of matrices and the vectors. So keep that in mind. Every time I write F, it will be a vector force vector. And every time I write a matrix, it will be in this stiffness and flexibility, it will be in matrix form. And it is time is for stiffness matrix time is displacement vector. Okay. Kx. Okay. So strain energy stored in our system will be strain energy stored. Strain energy stored in the system is, for example, if U1 is given as one half of, we know that it is given as one half of force vector transpose times displacement of kx. So since we are multiplying two vectors, so we have to take the transpose of the first, F transpose x. So if I will do one thing, I will do, so this is equation second, okay. I will do one thing here, substitute equation second here. So when I will substitute equation second, I will get u1 as one half of. So it will be k x over whole transpose times x. Okay. So I will get my strain energy u1 stored as one half of x transpose, because a b का whole transpose is called a transpose b transpose, one half of k transpose x. So let me name this equation as third. Okay. Again, we will write the strain energy in another form. Okay. We have alternate form of strain energy. We can write it as U2 is equal one half of uh, for displacement vector times force vector, because it will not change the ultimate quantity, because strain energy is a scalar thing. So I am taking the product of two vectors of equal dimensions will give a scalar, in fact. So it doesn't matter you are multiplying a b or you are multiplying b a. So that's why in the first step I wrote f transpose times x, and in the second step I wrote X transpose times F. So it should not change the final results. Okay. So here again, I will substitute equation second. Okay. Substitute equation second here. Okay. Again, here I'm substituting. It will result in U2 is equal to 1 half of. It will be X transpose and F is given by KX. Okay. KX. Okay. So it will be fourth equation. Since we are writing strain energy in two different ways, that is by first way is f of x, one half of fx, and another is one half of xf. So ultimately, it is not going to change the final value of the strain energy, is na? So that will be u1 is will equal to u2 from 1 and 2. From sorry, not from 1 and 2, from 3 and 4. 3 and fourth equation, we will come to the conclusion that if you see in the third equation here, if you see in third equation, you have u1 one half of x transpose k transpose x, and in u2 you have one half of x transpose kx. So only the thing that is differing between two equations, third equation and fourth equation, is k transpose and k. So for u1 equal to u2, k transpose should be equal to k. Okay, that is the required property. Okay. Okay, this is a simple thing. In another case, we can also do. So let me do quickly for the this one. I mean to say that flexibility matrix. How can I prove that flexibility matrix is this one? I mean to say symmetric also. I can do the same thing. So for second property second, I can show that uh, d where it is. I can show that d is equal to d transpose. Okay. So in the similar manner, I can write u1 is equal to 1 half of force vector transpose times displacement vector x. Okay. So here again, I am using the formulation that x displacement is equal to flexibility matrix D times force vector F. Okay. So this is 4, this is 5. Okay, fifth equation. So if I will incorporate this equation into this, okay, then I can get u1 is equal to 1 half of F transpose df. Okay, this is the one equation. You will get 6. Okay, same I can write it as u2 also. u2 is equal to 1 half of x transpose f. Okay, that's the simple thing. And again, using fifth equation here, it will be equal to 1 half of it will be equal to f transpose d transpose f. So it will be equation 7. Okay. But we again know that u1 will be equal to u2, and from 6 and 7 we can write uh, d is equal to d transpose. Okay, again I proved that stability and flexibility matrix is symmetric. Okay. So its flexibility matrix is symmetric. So this is one more thing, one more addition to your knowledge. Okay. So moving forward, we have orthogonality of modes. So I told you that while solving the eigenvalue problem for our multi-degree of freedom systems, that is the eigenvalue problem that we solve k minus omega square m is equal to 0. So we wrote the determinant of this whole matrix, that's k minus omega square m should be equal to 0. We get a polynomial which we then solved, and we got the eigenvalues for that one. And those eigenvalues corresponded to the natural frequencies of that system, and each eigenvector corresponding to the mode shape or mode vector of that corresponding mode. Now, two different modes having two different for the same system, but the modes are different, having different modal frequencies. There is a property or there is a relationship between these two modes, which we call as orthogonality. So, how we define this orthogonality, I will tell you in a couple of minutes. So, we will be studying orthogonality of modes. Orthogonality of modes. So I will start it somewhere else. Okay. Orthogonality of modes. Okay. This is the next topic that we'll be discussing in today's live session. And we will solve some problems later on if the time will be available at the end of this session. Okay. So I already told you that. So for example, if we have a system like this, multi-degree of freedom system, wherein we define it multi-degree of freedom system as m x double dot plus k of x is equal to 0. So we are considering only free vibrations here. We then assumed that the solution of this thing will be x of t, assumed that it will be some x times sine pt. Okay, p of t, or we can turn this as phi n. Okay, let it will be phi n. Okay, some mode vector phi n. Okay, so when we find x double dot for correspondingly x double dot, we get minus p square x of t. Okay, original displacement. So when we will substitute back to this equation, we get this beautiful formulation like this. And x double dot, we get p square m plus times phi n plus k phi n, not x of t. So it will be p square and phi n. It will be phi n, and it will be sine pt. P square sine pt should be equal to 0. So for this to have a solution, uh, minus p square m plus k times phi n. Phi n is a matrix. Sine pt, if sine pt cannot be 0, okay, So this should be equal to 0. So for this system to have a solution, it becomes an eigenvalue problem like this one. It reads like this: p square m times some vector phi n should be equal to k times phi n. Okay, this is a thing that this becomes an eigenvalue problem. Okay, this is an eigenvalue problem that we have to solve to get the things. So we can write this as uh, k minus p square m times phi n should be equal to 0. So for a non-trivial solution, we need that determinant of k minus p square m should be equal to 0. I already told you this is known as characteristic equation. Okay, this is known as characteristic equation. This thing. So for every eigenvalue, characteristic equation. Each eigenvalue correspond to model frequency and each corresponding eigenvector correspond to mode shape. Okay. In last class, I solved 2-3 multi-degree of freedom system problem where I showed what we mean by model frequency and mode shape. So consider we are having two mode shapes. Okay. So for example, we are having one mode shape uh, phi of n. It's a mode shape corresponding to the natural frequency p of n. Okay. Mode shape corresponding to p of n, natural frequency of p of n, and another mode p of n we will consider. It's a mode shape corresponding to p of m. Okay. So these modes are totally independent of each other, both because both are having different natural frequency or different model frequencies and different mode vectors. Okay. So what orthogonality of modes reads? Orthogonality of modes states that uh, if we do this phi in transpose times stiffness matrix of the system times phi m. Okay. Or we will term this as r phi r. Okay. It will be convenient for us. Phi r. Okay. PR. So it reads that phi n transpose k phi r is equal to 0 and phi n transpose, sorry, it's n here. Okay. Phi n transpose m phi r. Okay. is equal to 0. This is the model orthogonality. Okay. So I'm just stating a mathematical statement here, what we mean by orthogonality of modes. In the end of this topic, I will give you the physical essence, what it actually means. Let me first prove how it is true that phi n transpose k phi r is equal to 0 or phi n transpose m phi r is equal to 0. Later on, at the end of this topic, I will tell you what is the physical essence or what it physically means that phi n transpose k phi r or phi n transpose m phi r is equal to 0 and why. So you just keep in mind it is orthogonality. It's only known as orthogonality because in the vector algebra we have studied that if we take the dot product of two vectors that are orthogonal to each other, their dot product is zero. Same in the you can term same analogy to that. Here we are having two mode shapes, or it are in terms it are just the vector coordinates or the vectors. We are just taking their dot product with some more additional terms. For example, we are taking stiffness matrix and mass matrix also, but you can relate it to that. That's why we call this it is an orthogonality property. Okay, orthogonality property of mode shapes. Mode shapes. So one more thing, mode shapes satisfy the property. Satisfy property. I already wrote it here. They satisfy the property p square m phi n is equal to k phi n. Okay, that is k phi n is equal to p n square m phi n. Okay, this is, let me term this as 8. Okay, equation 8. So if I pre-multiply it by phi r transpose. Okay, so from both sides we will multiply by phi r transpose k phi n is equal to pn square. Since it's a scalar, we can take it out. Phi r transpose m phi n. Okay, this is one thing. And so if we take the transpose on both sides, okay, we will take this. So taking transpose on both sides, we will get the equation like this: phi n transpose, since k is symmetric, it will be k again. Phi r transpose, whole transpose will be phi r. Okay, this is one thing. And for scalar, there is no use of transpose, p n square, and it will be phi n transpose m phi r. Okay, so let us term this as equation 9. Okay, okay. So we wrote this since more mode satisfy the property for mode phi n. Okay, we can write for mode phi r. Okay, same mode phi r. We can write for mode phi r. We can have k phi r is equal to pr square m phi r. Same property. Okay. This is 10. Okay, this is 10th equation. Okay, so to this equation we will multiply, pre-multiply by phi n r, phi n of transpose. Okay, so we will get phi n transpose k phi r. It will be, since nothing is to do with this scalar, we can take it out. It will be phi n transpose m phi r, m phi r. Okay, m phi r. So it will be 11th equation. So if we look at equation 9 and 11, equation 9 and 11, if we say that if in 9 LHS is phi and transpose k phi r, and in 11 it's also phi and transpose k phi r, so both RHS will be equal. Okay, so we can write p n square phi and transpose m phi r is equal to pr transpose, pr, not pr transpose, it's pr square. It is pr square phi and transpose m phi r. Okay, so if we can take it to the left hand side, pn square minus pr square. So pn square minus pr square times phi and transpose m phi r with different modal frequencies and modal mode vectors. That's phi n and phi r. So in any case, p of n is not equal to p of r. Okay. So uh, phi n and phi r are totally independent. So in no case P of n is not equal to P of r there, which implies Pn minus Pr is never gonna be equal to 0. So in order to satisfy this equation, okay, we necessarily have to equate P of r transpose m phi of n. This not phi of r, this phi of n transpose m phi r should equal 0. This is simply the model orthogonality. Okay. Okay. Model orthogonality property of modes. So this is the thing we needed to prove. We can also prove that phi and transpose k phi r is equal to 0. We have to follow the same formulation. We can also prove phi and transpose k phi r is equal to 0. We can also prove that. Okay, orthogonality of natural mode. So this was the thing. So we will take 5 minute break first. So I proved that proved that phi n transpose m phi r or phi n transpose k phi r is equal to 0. But it's just a mathematical formulation. So what if anyone tells you what actually it means? So what actually model orthogonality is? We will just learn about that. What orthogonality is, okay? So if somebody tells you, what do you understand by this orthogonality? You should be able to answer. So we will be studying that one. So orthogonality, we can take different implications of this concept, model orthogonality. So implication one, we can say that model orthogonality refers that work done by the nth mode inertial force in going through earth mode displacements is zero. So for example, we have two different modes, n mode and r mode. So the nth mode inertial forces, if they go through the displacements which are uh, obtained by earth mode. So if we take the work done, total work done, that will be zero. Okay. uh, I will write it here, implication first. Implication first is work done by earth mode, nth mode inertial forces, inertial forces forces in going through earth mode displacements, going through earth mode displacements is zero. Okay. Okay. So let me prove that. How we can prove that work done by nth mode inertial forces in going through earth mode displacement is zero. So let's consider a structure vibrating with nth mode displacement. Structure vibrating with nth mode displacement. So our structure is currently vibrating its nth mode. So we can write its displacement x of n, displacement vector x n of t will be equal to q n of t. Okay. Qn of t times phi n. Okay, so I have just written that we write here now x is equal to phi n sine omega t plus some phase angle phi. So I'm just writing this is a displacement vector x and this is its time variation. I'm writing it by Qn. Okay, it's time variation in nth mode. Okay, this is a simple thing. And it's x here. Okay, I'm just replacing these things, qn of t phi of n. So correspondingly acceleration of this mode will be x of t will be equal to, so it will be time varying double derivative up to qn of double dot phi n. It's only phi n is also only dependent upon the space vectors, that's the coordinates, so it will not have any differentiation with time. So inertial force in the nth mode then will be, we know that inertial force in nth mode. Inertial force in nth mode will be, so I am denoting it by F inertial and it is in nth mode. It will be, we know that inertial force is given by mx double dot and it is opposite to the motion of the vibrating structure. So it will be, for the motion displaced out of this, it will be negative times mass times acceleration of the system. Mass matrix times acceleration vector of the system. So x double dot n of t. Okay. So if we substitute, this will be 12. Substitute 12 here, xn of t. So we will get our inertial force in nth mode. Okay, inertial force in nth mode will be then equal to minus m mass matrix times phi n q n double dot of t. Okay, so let me denote it as 13th equation. Displacement of structure. So now consider structure are vibrating in earth mode. Okay, we can similarly write the displacement in earth mode xr of t will be equal to qr not double dot qr of t, that's the time varying component, phi r. Okay, it's the same thing. Okay, qr of t phi r. So now we'll work done, we will find the work done by nth mode inertial forces. Okay, Fi of an nth mode or inertial forces in going through displacements by earth mode. Okay, x r of t displacement. It will be given as work done will be simply given as Fi of n. Since these are two vectors to be multiplied, so we have to take the transpose of the first one. It will be x of xr of t. Okay, these are two vectors. Okay, since these are two vectors, and we will substitute equation 13 into it. Okay, here when we substitute 13, it will be minus m times phi n q n double dot of t, this one thing, and it will be transpose, and it will be q r of t, and it will be phi of r. Okay, it will be phi of r. So we will rearrange our things like this. So it will be minus phi n transpose. Okay, it will be phi n transpose m transpose will be again m. It's q n double dot of t. It's not a vector, it's just a time varying quantity. It's q r of t times phi of r. If we collect the like terms like this one, we will have things like q n double dot of t, that's the acceleration component, time varying acceleration component. Q r of t, that's another time varying displacement component. We will have our phi n transpose m phi r. So when this work done will be 0. If we assume that phi n transpose m phi r is equal to 0, if we uh, assume phi n transpose m phi r is equal to 0, so correspondingly our work done will be equal to 0. So what our implication first states that of model orthogonality for two modes n and r is that work done by inertial forces of nth mode in going through earth mode displacements is equal to 0. Okay, this proves our first implication. Second implication similarly can be proved like that work done by equivalent static forces associated with displacements in nth mode and going through earth mode displacement is equal to 0. Okay. Implication second. Implication second we have, can write it as work done by equivalent static forces done by equivalent static forces of nth mode through earth mode displacement displacement is 0. Okay, This is the one thing. So we can prove it quickly as we already wrote it. We can write equivalent static forces. Equivalent static forces. Equivalent static forces F of S, and it is in nth mode, okay? It is static force is actually the restoring force, that is K stiffness matrix times displacement. Xn of T, okay? So Xn of T we have to replace it by K Qn of T phi n of phi n, okay? So we can write work done as work done W is equal to equivalent static force in nth mode and its transpose times xr of t as it's going through the displacement by rth mode. So it will be equal to qn of t phi n transpose k, and it will be qr of t phi of r, okay? So collecting the like terms, we have qn of t, qr of t, and we have phi n transpose k phi r. So we will say that work done by equivalent static force in going through the displacement by in nth mode in going through displacement of rth mode will be zero only if we assume this quantity phi n transpose k phi r is equal to zero. This proves our second implication that work done by equivalent static forces associated with displacements of rth mode is equal to zero. So this is actually the physical meaning of orthogonality. So I think it's enough for today. I think we already covered a good amount of topics. So thank you everyone for joining. It's all for today. Thank you.